Okay, so um, let's go to the second part of my talk today, which is related to the supermassive black holes that I talked about yesterday. But this talk will be focusing more on the relativistic jets, which come out from the supermassive black holes and their physical properties, as well as their astrophysical implications, that what we can learn from these jets. So this will be the main theme of my talk today. And I thank all of you for having joined in this session. So let's go ahead and see some mysterious or exciting things about these relativistic jets in the astrophysical domain. So let's go ahead and first let us, uh, uh, this presentation is not correct. एक minute, 1 minute. I think this presentation is something. 1 minute. I think it's a new presentation. Oh, sorry, can you hear me now, Sagar?
Yes.
Okay, sorry about the interruption. It was a wrong file, so we had to convert into. Sorry about it. So now we are through it. So as I was telling you, so today's talk will be on relativistic jets. So first, we should know what is a relativistic jet. What are the properties of relativistic jets? So actually, relativistic jets are actually the streams of plasma. There's nothing very astrophysical about them. They're actually physics. Entire thing is like a particle physics. So there are streams of plasma which propagate these particles in this stream like the bulk velocity. The entire plasma stream propagates with a speed which is very close to the speed of light. So that's why they're called relativistic. And I'll give you some evidence that why, from how we can prove that they are moving at relativistic speeds. And of course, they're emitted by the central black holes uh, of some active galaxies. And notably among these galaxies are, as we discussed yesterday, radio galaxies and quasars. And also these jets are commonly found in some other astrophysical objects like neutron stars or newborn stars, like what is called big haro objects. So you can see this jet phenomena quite commonly observed in astrophysics. And these relativistic jets in active galaxies can be extremely large. They can go up to megaparsecs scales. So I'll give you some information at the end if there is time about our research in this domain. So yes, so these are plasma jets with extremely powerful relativistic particles, extremely energetic relativistic particles which propagate near the speed of light. And supermassive black holes in the galactic central regions, that is the AGNs, produce the most powerful jets. Obviously, we can see this in astrophysical domain through X-ray observations or radio observations. But similar jets can be found on a much smaller scale associated with neutron stars or accreting binary systems, which are also small mass black holes accreting mass from a companion star. So here we don't have a companion star. We feed gas into the black hole through an accretion disk or through a stream of gas. But we don't have a companion star. But we can have a companion galaxy, which is much more complicated situation than what we see in the case of a X-ray binary system. Okay. So general thinking among astrophysicists is that the formation of relativistic jets is the key to explaining the production of gamma ray bursts. So these are the extremely powerful sources of gamma rays which are produced at the rate of 1 per day, almost 1 per day gamma ray burst takes place somewhere in the universe, and extremely energetic streams of gamma rays can be seen coming out from these sources. So these objects are certainly connected with supermassive black holes, formation of supermassive black holes, and the production of gamma rays tells you that there are extremely relativistic effects are at play in these objects. And in fact, some of the objects in some of the jets that have been seen in relativistic domain of gamma rays or quasars have speeds that the Lorentz factor of V by C factor, the beta factor is like 0.9999 C, which is like Lorentz gamma factor will be something like 10 to 20. So it's extremely large, 5 to 10 or even larger. So these are some of the fastest objects that you can see in the universe. These objects are extremely massive also. So you can imagine that there will be tremendous amount of energy associated with these outflows, because something is moving at the speed of such high speed at 0.999 C and carrying so much of mass as essentially momentum. So they'll be very, very energetic. And of course, the jet speed is close to the speed of light. So therefore, all the effects of special relativity. Here we produce the jet from magnetohydrodynamical process in the general relativistic domain near the black hole. But actually, when the jets are away from the black hole, they are all dominated by special relativistic effects. So here, both the effects can be seen very beautifully. So these jets are the laboratories where you can study or test the theories of special relativity as well as general relativity. So that is the use of these jets. So they are actually the fantastic laboratories produced by nature, and which cannot be, the conditions prevailing in the jets are so exotic that it is extremely difficult to produce these kind of conditions in laboratory jets, like particle accelerators or whatever plasma physics processes you generate in the laboratory are far below the energy level of these jets. So they can be extraordinarily powerful as well as fast moving jets. So what is the source of this energy? How you can generate so much of energy as well as channelize this energy in the form of a jet? It's a matter of, still a matter of great debate, as well as there are a lot of controversies about this. So the issue is still open. So there are lots of possibilities of research in this field, and the new generation of radio telescopes or X-ray telescopes which are being made or which is already existing can be used to answer some of these questions. So, okay, so let us go into some historical ideas of relativistic jets. So the first relativistic jet was discovered almost 100 years back by Curtis in United States. So there he photographed a strange phenomenon which is a straight blue ray-like object feature coming out from the nucleus of this galaxy called Virgo A, which is very famous nowadays because the first black hole shadow has been discovered in this galaxy. So the connection of this galaxy with modern astrophysics goes back to 100 years. And he stated in his paper that is a curious straight ray apparently connected with the nucleus by a thin line of matter. So that's all he described this jet as having this kind of morphology, but he had no idea whatsoever that what can produce this kind of feature. Later, after about a decade, I think, Walter Baade and Minkowski in United States again noted, restudied this jet, and they noted that there is several strong condensations, as you can see on the picture on the left hand side, that this jet is not continuous. There are several condensations in this jet, essentially the knots, what radio astronomers call knots, and there are some bright and dark features. So it's like a periodic structure in the jet. So these jets are never continuous. They are all astrophysical jets are periodic, or they have a knots or bright regions succeeded by dark regions, again bright regions like this. And there are extremely bright shocks also in this that you can see here. Is a shock-like feature. There's a parabolic structure here, which is thought to be a shock front. So the matter is moving much faster than the speed of sound in the local medium. That's why you see the supersonic shocks in these jets. So these are extremely important laboratories for magnetohydrodynamical shocks, relativistic shocks, and all kind of particle physics processes can be understood if you study these jets very thoroughly. So that's the importance of these jets. These are not just for exotic objects in the sky, but they are the laboratories which all physicists must also connect, because there is a lot of effort is going on right now to obtain fusion plasma and plasma acceleration processes, plasma containment processes. So all these processes are happening in these jets, and there is a complete very little understanding how these processes are happening in these jets. So that is where these jets are useful laboratories for astrophysical and laboratory plasma also. Okay, so here you can see a Hubble Space Telescope image. It's a modern image. It's a spectacular image, but if you see the image in radio, it will look very similar. Only the jet will extend far beyond what you are seeing in optical light, but the jet will be visible in radio also. So this is the somewhat more modern information that this galaxy core contains a supermassive black hole which weighs something like 7 billion times the mass of the sun. So this is an extremely heavy black hole, and this mass has been obtained recently from the Event Horizon telescope. So they have been able to image the photon ring, or the region where the photons are in an orbit around the black hole, and measuring that dimension of that ring, this mass has been obtained, something like 6 to 7 billion solar masses. And this is one of the most massive black holes known in the local universe. But what is very strange, I would like to point out here, which I will describe in more detail, that you can easily see that this jet is completely one-sided. Even if you see it, it's a very sensitive observation, there is no trace whatsoever of a counter jet here. So this is completely one-sided jet. So now the question is whether the jet is really one-sided or it's an optical illusion produced by special relativistic effects. So the answer is no, the jet is actually bipolar. There are two jets in it, but due to special relativistic effects, which I will describe just now, you cannot see the counter jet, but you can see the front jet, which is forward jet, very clearly. But the reverse jet or a counter jet is completely invisible, even with a sensitive observation like Hubble Space Telescope. So that tells you that these jets are really moving near the speed of light. Otherwise, you cannot have this effect. So what is this effect? This effect is extremely important for study of astrophysical jets, particularly jets from quasars and radio galaxies. So this phenomena is very well known in special relativity, which is called Doppler effect or Doppler boosting or relativistic boosting of radiation. Or another name for this phenomena is, which is more simple name, is called aberration of light. So essentially, if you emit a light in the laboratory frame in certain towards some axis, say towards x-axis, and then if there is a frame moving relative to this laboratory frame with some speed v by c, then there will be transformation of angle. Essentially, the stream of light which is emitted in the laboratory frame at some angle theta will not be visible at the same angle, but it will be seen as a smaller or larger angle depending on the velocity, which direction you are moving. So this is called aberration of light, which is very well known process in relativity. But here you can see very, very strongly this effect. So what is shown in the middle right hand panel, first this panel, that you can see an arrow. This is in the direction in which the jet is emitted, and the color of the light which was emitted was a monochromatic light. It was not a colored light. It was something like a yellow colored light that you can see here in this perpendicular direction. But now what you are saying, this jet is moving something like near the speed of it is written 0.9, something like 0.9 c, 0.89 c. So this is the classical Doppler effect. What I have plotted here on the right hand panel is a classical Doppler effect without taking into account of the relativity, without Einstein's theory being invoked, just classical Doppler effect. But you can see that if I see this jet from the forward direction, then I will see the light green color. And if I see the jet from the back side, opposite direction to the direction of the velocity of the jet, I will see the red color. And if I see the direction perpendicular to the jet, I will see the normal color of the jet, which is yellow. But you can see this cone of this color change is very, very broad in non-relativistic classical domain. But when we invoke relativity, there is a further reduction of this cone by a factor of gamma, which is Lorentz factor, 1 upon gamma times. This cone will shrink by 1 upon gamma times. And on top of it, there is a shrinkage of angle, which is aberration angle. On top of it, you can also see the color of the light is now very strongly bluewards in the forward direction. You can see it is almost violet. Although the color of the light which was emitted from the in the stationary frame or the laboratory frame was yellow. It was monochromatic. But I will see this light is an ultraviolet or blue color light. And then as I move away from the jet axis, I see I will go towards longer wavelengths till I reach this yellow domain again near the perpendicular direction. But you can see even this perpendicular direction is slightly upwards, not exactly perpendicular. And on the back side of the jet, I will again see Doppler shifted, deboosting. Essentially, the cone is much broader on the other side. So you can, I have not plotted the cone of emission, but you can see it is very, very broad and the color is reddish. So you can see there is a fantastic change, of color as well as angle of emission between two frames. So this is what is called relativistic Doppler effect or Doppler boosting due to the plasma moving at very high speed relative to the observer. So on the left side plot, there is this graph. This effect has been plotted by putting actual simulation or mathematical quantities have been simulated. This Doppler effect as well as its boosting effect has been simulated here. So this red arrow is the jet direction, and you can see them some circular grid pattern here. There's 10 to the power 4 written here, 10 to the power 3, 10 to the power 2, 10. So these are Doppler boosting factors. That means not only the color is changing, the intensity, the specific intensity or the intensity of the radiation is also coming higher and higher. So here is a 10 factor of 10 amplification, then factor of 100 amplification, then 1000 and 10 to the 4. And here this colored ellipses or colored contours are, this is 0.99C yellow, then blue 0.99, then green 0.98, and then light blue 0.9 and 0.5 violet. So you can see as I increase the speed of the jet and it comes to the relativistic domain, the emission is getting concentrated in narrower and narrower cone, as well as it is getting amplified in the forward direction. So that means if I see from this direction, to get an amplification of 10 to the power 4, I need to be here. But if I see in this direction, I will get a much higher amplification. And if I am off the jet, like at a large angle to the jet, I will get very little amplification. You can see nowhere I can reach 100 or 1000. So this is extremely important effect which changes everything in relativistic jets, because what you see is not what is being emitted. It's completely modified by the effects of special relativity. Neither the color of the jet, that is spectral energy distribution that I am seeing, is same as what is being emitted. Neither the emission angle is the same. I am seeing the jet as extremely high energy as well as being emitted in a very, very narrow cone. So this is the reason why we cannot see the counter jet, because the forward direction, I plotted this graph only in the forward direction. But if I plot in the opposite direction, it won't be symmetric like this. It will have some other shape. So that may be possibly it is symmetric, but it will be not visible to me because I am seeing in the forward direction. But the back side will be, if I see from the front direction in my frame, this will not look symmetric. It will be completely asymmetric. Only in the source frame, this pattern is symmetric. But in my frame, the observer frame, this pattern is not symmetric at all. It is highly asymmetric. So I will see very different picture from the opposite direction, seeing from this side of the jet, but I will see completely different picture. So essentially all the intensities will be hugely reduced by the very large factors, as well as they will be hugely red shifted. So another factor which will come in my observation, that I will not be able to see the jet in my spectral window, neither I will be able to see the jet in my sensitivity window. So that's why this jet will vanish from the opposite direction. So, okay, so this is a beautiful phenomenon. I must say that you must realize the importance of this, because this is not normally seen. This is not normally seen in normal laboratory experiments. Only in particle physics experiment, when you have a synchrotron or a very high energy particle accelerator, you can see this effect. Essentially, what is called synchrotron radiation is a consequence of this fact that the radiation from an accelerated particle like an electron is forward boosted, and In the reverse direction, it is deboosted. So I will see the forward direction of the radiation extremely strong, but I will not be able to see a strong radiation coming from the opposite direction. So this effect, when the particle accelerators have magnetic fields and energetic particles are gyrating in magnetic field, I will see it as a synchrotron radiation. So this effect is also present in the radio galaxies and quasars. But here I am only talking of relativity and of the that is transformation of angles and colors. I have not put any particles into this problem right now. Neither have put any magnetic field, which I will put later on. So here you can see a coherent beam from a laser, and it has got very similar characteristics, because the laser does not emit in the opposite direction, because you block it by a box or something, and we have a mirror, semi-transparent mirror, whatever. So you don't want the jet to be two-sided, but you want the jet to be one-sided. Jet means it's like electromagnetic jet now, but it's highly coherent beam of light. But here it is also partially coherent. The coherence also increases by this phenomena, but I'm not going into that. So this is just for comparison. So here we can see M87 again. So here is the optical picture on the upper right side, upper panel. And again, this picture is taken from Hubble Space Telescope. And if you use a radio telescope, then you will see a very different picture. So you can see these pictures almost on the same scale. So the nuclear emission, or the AGN nucleus, is clearly visible, as well as you can see the radio jet coming out here. The structure of the radio jet is identical to the optical jet. But then optical jet fades away beyond this point, but the radio jet continues or feeds into giant lobes of plasma. So this is very, very strange situation, that why we don't see this radio jet in X-ray or optical, but we can very clearly see this byproducts or the waste products of this radio jet in radio domain. So you cannot see what happened to the jet when it lost all its energy. That's why it has disappeared. It has lost all its energy to emit in ultraviolet or blue light, but it's still emitting in radio wavelengths. So that means there is some difference in the energy of the emitting particles. So these are not the same electron which is producing this jet as well as this jet, but they are co-spatial, but there is a change in the energy. So this is the characteristics of synchrotron radiation. So the light that you are seeing in the upper panel, the HST picture, is synchrotron radiation, as well as the light you are seeing, electromagnetic waves that you are seeing in the lower picture, radio galaxy, in the VLA picture, it's also synchrotron radiation, but their Lorentz gamma factor or energy scales are very different. So these are much, much higher energy particles which produce ultraviolet light and UV light, blue light, and these are low energy electrons. So this is you must have studied this in synchrotron radiation. I think somebody must have covered this radiative processes. So by connecting it to, you can understand. So so this is essentially a function of magnetic field as well as the energy of the particles. So the high energy particles in higher magnetic field will generate shorter wavelengths, that is high energy photons. But the same energy particle, if you put in a lower magnetic field, it will generate longer wavelengths or lower energy photons. So that's why you can explain this difference by comparing the energy of the particles as well as the magnetic fields. So then it becomes extremely useful tool, these jets and these sources, to understand how the particle energy is evolving in spatial direction as well as in temporal direction. I mean, whether it is changing with time, if it's a variable, or if it is propagating outwards, how the energy is changing, whether it's losing energy, whether it's gaining energy. So you might see here, there is in the shock, there is a brightening here also. So suddenly the synchrotron radiation has picked up, become brighter. That means there's a particle acceleration going on here. And if you take the spectrum of this radio spectrum, then you will find this part is flatter spectrum. That means there is acceleration of particle in the red zone that you are seeing. And here there is a brightening in UV light also, you can see. So this is very, very useful in that sense. Okay. So there is another spectacular image here, which is a superposition of Chandra X-ray radiation, which is plotted in blue color, few kilo electron volts, And in red color, I have plotted the VLA, that is very large array radio synchrotron radio emission. This is also synchrotron radiation, but may not be fully synchrotron. But this is certainly synchrotron, red. And now you can see this radio jet or a relativistic jet can be traced all the way from the nucleus to the dissipation point or the hot spot, which is at the end of this jet. There is another huge brightening in X-rays, and there is a lobe associated with it. That means the jet is going out and hitting some medium here and getting decelerated, and all the energy is suddenly dissipated in the form of a shock, where it can again become a very bright source, as you can see here. And afterwards, it's all the low energy electrons are losing, I mean, all the electrons are losing energy because that's why it is so bright. And then they are diffusing out in the form of two giant lobes. And you can see there is no counter jet visible here, but there is a hot spot like feature visible here. That means this jet is present, but not visible again. That means just this jet is extremely relativistic, moving at a very high speed relative to the speed of light, and going almost at the same speed up to here, because you cannot trace this jet ever up to the end of it. But you can see the diffuse radio lobes, which are lower energy electrons. And there is no kinetic flux. That is, the forward momentum has been lost. They become like a turbulent flow. That's why you can see is being visible to you, because that Doppler boosting factor is no more here. Essentially, that's the secret of this source. That's why it looks so peculiar. But every feature of this source can be understood from the point of view of synchrotron radiation as well as relativistic effects. Now here, I think you had heard about these active galaxies and related objects from Professor Saikia's lecture. So I'm not going into much details, but just for completion, I'm showing you again the similar pictures. You can see this beautiful radio galaxy called Centaurus A. And from the center of this, you can see this X-ray jet coming out like a fountain and then getting dissipated in these giant lobes. So this is X-ray on the right-hand side, then the radio. So this is a three-color superposition on the left-hand side. So on the right-hand side, this is decomposed into various wavelengths. So first is X-ray, then is radio, and then optical. So you can see there is no trace whatsoever of this jet in optical light. That means these jets don't produce huge amount of optical light. They are completely invisible in optical domain. But it's not that all of the every jet is invisible. Some of the jets are seen in optical light also, but they are very, very small region of the jet can be seen, not the entire jet. But you can see the X-ray jet can be seen up to this point, but not beyond this point. But the radio, as I described, can be seen much further out, and all the exhaust or waste product. So it's not very good for the radio astronomers, but they are seeing actually the waste product of the jet. So after it having lost all the energy, what is left out is visible in radio astronomy. But it's not correct. I will just show you. There may be some interesting things seen in radio from the very nucleus itself. It's just like a joke. Okay. So what is the active galactic nuclei? So I think it has been told to you. So there are various categories of active galactic nuclei. So these are the galaxies which have an extremely powerful source sitting in the core of the galaxy. And this is a source of non-stellar emission process. So these emission does not come from stars, but some exotic particle acceleration processes. And they are visible in UV, infrared, radio, and X-ray light mostly. Now you can see them in neutrinos also and gamma rays also. So I will just show you one picture, which is, it has been detected in ultra high energy neutrinos also. So that means this central black hole accreting its material from the host galaxy, as I told you yesterday's lectures, proposed by Lyndon Bell in 1969. So this was a very, very important work by Lyndon Bell, which has changed the field. So this is a classic paper. So now quasars, there are various categories of active galactic nuclei, AGNs. So there's a whole zoo of AGNs. So if you go to any textbook, then you find there are lots of objects. But basically they are all related of various type and various morphology and various energy. That's the only difference. So main categories are quasars, then Seyfert galaxies. So quasars are most luminous objects, with broad emission lines, and they are very distant sources, and some of them are extremely strong radio sources. Then Seyfert galaxies are fainter version of quasars. They are not so bright, mostly identified in local spiral hosts, and there are two types of Seyfert, Seyfert 1s and Seyfert 2s. So Seyfert 1s show broad emission lines, and Seyfert 2 shows narrow emission lines. It may show both actually. One may show both, narrow and broad. This only shows narrow. Then you have starburst galaxy. I'm sure Professor Shaikia will cover it today or yesterday. He covered. The extreme star formation is going on in these galaxies, in addition to a black hole accretion in the nucleus. So there is a starburst AGN connection, which is still not fully understood. What is the connection between a star forming galaxy and the AGN that it hosts? So this is one of the very key areas of research. So there is some connection between starburst and AGNs. So most of the AGN galaxies, some of them are highly starburst galaxies also. Then there is some peculiar type of galaxies known as radio galaxy. They produce excessive amount of radio emission, but not much of other type of emission, like quasars. So they are very peculiar nature. They are called radio galaxies. They are mostly found in elliptical galaxies, not like Seyferts. And host of these radio galaxies are giant elliptical galaxies. Because the elliptical galaxies have bulges, and yesterday I could not tell you, there's a connection between giant supermassive black hole and bulges of the galaxy. So giant supermassive black holes are found in bulge-dominated system. The stronger the bulge, that is the more massive and more brighter is the bulge, more massive will be the elliptical galaxy black hole. So that's why you have these radio galaxies coming out in this elliptical galaxy, associated with elliptical galaxies. So similarly, radio loud quasars are also found in elliptical galaxies, but some of the quasars which are radio quiet, they don't produce much radio emission. They may be found in spiral galaxies or merging galaxies. And most extreme form of these starburst galaxies are ultraluminous infrared galaxies. So these produce huge amount of infrared radiation, which is associated with mergers also. But their most luminous output or the most energy output is in the near infrared to far infrared region. So these are called ultraluminous infrared galaxies. Now, this is a cartoon. You can see how a jet, radio jet or a relativistic jet is formed. I will give you some information, more information about this. But this is a cartoon. There is a accretion disk around the black hole, which is sitting in the dark region here. And this accretion disk is rotating at a very high speed near the black hole. It almost reaches the speed of light, or half of the speed of light, near the event horizon. And as you go out, the speed goes down. So it gets hotter and hotter in the central region due to dissipation of energy in friction. So there is a differential motion in this disk. So inner region are moving faster and outer regions are moving slower. So that creates a frictional effect. And then the disk is getting very, very hot in the central region, as well as transfers angular momentum outward, so that it allows the gas to fall in. And once it falls into the black hole, then there can be some other effect, which I will just tell you. This, like magnetic fields can be twisted. And then along this twisted magnetic field, you can have this bipolar emission of relativistic particles, which we call jets. So yeah, so some of the gas is driven out into collimated jets focused by strong magnetic fields. So you need magnetic fields to form jets. So I will just deal with this right now after some time. So here is a beautiful artist picture, which I like very much. You can see this picture in Science magazine. It came on the cover of Science magazine. So perhaps this is how it will look like, but it's an X-ray binary star. So this is another star sitting here, which is feeding gas into this black hole. And you can see this is being channelized through some stream and through Lagrangian point. That there is, this is a Lagrangian point or some equipotential surfaces that you can see in IUCAA compound also. So this is the two-body, Kepler two-body problem, rotating system, two-body system, where the gas is being transferred from the star to the black hole. And this is going into the accretion disk. And then this black hole is also producing relativistic jets. Okay. So how, so this I dealt with, I won't go into. So we know about Schwarzschild radius, 2gm by c square. So what is the Schwarzschild radius for the sun? It is 3 kilometer, very small. So you have to compress the sun into a sphere of 3 kilometer to make it a black hole. But for a supermassive black hole of 1 billion solar mass, the Schwarzschild radius is not so small. It is very small compared to the galaxy, but relatively much bigger. So it is something like 3 billion kilometers. Because it is 3 kilometers, so I can just scale it by mass. So 3 kilometers into 1 billion. So very easy calculation, 2gm by c square. So it will be 3 billion kilometers or 0.00097 parsec. It's extremely small, so like a 10 to the power minus 4 parsec. Sorry, this 10 to the power minus 1, 2, 3, 4. Yeah, 10 to the power minus 4 parsec. 10 to the minus 3 to 4 parsec, yeah, or 10,007 light seconds. So essentially the light will take 10,000 seconds to fall from the edge of the Schwarzschild radius to the black hole, the center of the black hole. So that's what it means. So this is something like orbit of Neptune or something. So this will be like a total solar system, dimension of solar system. So this black hole will fit inside the solar system comfortably, a billion solar mass black hole. So this I will not go and produce. I explained this yesterday, how you produce energy from the black hole. And here you can see some homely version of jets that you can see in your kitchen. So here there is a pressure cooker. And you can do this experiment. Generally, people cook food in the pressure cooker and allow it to cool for a long time till that this steam dissipates. But you can do some daring experiment. If you suddenly open this safety valve with some boiling water inside, then you can see a beautiful jet going upwards. And then you can see this jet is looking like a relativistic jet that you see here in the radio domain. And this is like a two-sided jet. Sometimes this pressure cooker will generate two jets on both sides. So this is similar process which is happening in the kitchen. And the very similar looking jet is happening in black hole, around the black hole. So that shows the unity of physics. So why does this jet looks very similar to this jet? So perhaps there are lots of laws of physics which are similar, which we don't understand. So there has to be a nozzle like this. You see here in the pressure cooker. So there is a nozzle here, certainly, through which this high pressure plasma is escaping, like a high pressure steam is escaping. Now you can see this jet is collimated after some time, and then it's losing its collimation. Similarly, you can see this jet is collimated after some time and losing its collimation. And you can see there are some instabilities or some wave-like features at the edge of this jet. You can see the similar wave-like features at the edge of this jet. So I showed this picture to bring home the point, bring home literally the point that jets are jets. They behave in a very similar manner, whether it is coming out from a pressure cooker or coming out from a black hole. Their behavior is very, very similar. It's not that they are something very, very exotic. So if we study these jets in our laboratory or our kitchen or some homely domain, then perhaps we can understand these jets much better. And you can see again here in this jet, radio jet, which is a radio galaxy 3C31, the relativistic beaming effect. Because the inner jet is very, very bright up to this point. This jet which is coming towards you, while the counter jet is not so bright. But afterward, you can see jet luminosities are similar because it has lost its velocity, high velocity. Okay, so it's a beautiful process, huh? 10 minutes. Okay. So here is another peculiar type of object which was discovered from GMRT observation. So this was done by one of my I was co-guide of the student Biju, who is in Kerala right now, and we had he discovered this jet through GMRT observation. So you can see GMRT can produce extremely beautiful pictures of the jet. So this jet happens to be an extremely large scale jet because the dimension of this jet is something like a megaparsec. So GMRT can do very good work in imaging these jets. So you don't need VLA, or you can use GMRT, our own telescope, and it can produce spectacular pictures. So okay, so I will skip this. And now I can tell something about the formation mechanism of these jets. So here is the highest resolution picture of a radio jet ever produced. So this is again M87, which is a very favorite object of astrophysicists. And you can see 2 centimeter wavelength. So this picture is taken at the wavelength of 2 centimeter using VLBI, very long baseline interferometry. So this picture has a resolution of something like 0.25 parsec, of half parsec or something less than that. So this jet is resolved beautifully. You can see the bright region at the left, and then you can see this jet having a dark core, and outer edges are bright, but the inner edges are dark. So this was not known earlier. The jets are not uniformly illuminated. They have some structures, and you can see a lot of structure is visible in this jet. So the question is that how supermassive black holes manage to produce such highly collimated outflows. So this is the physical question, astrophysical question, that what mechanism is involved. Now we have to go to the astrophysics of the formation of jets. So what mechanism is involved in creation of these jets? So this is one of the very interesting areas of astrophysics, which is still not fully resolved. So it is thought that these jets are connected with spinning black holes, not stationary black holes. So what is a spinning black hole? So the geometry or the space-time structure around a spinning black hole is shown on the right-hand panel here. So this is a curved black hole, curve metric. So this has got a very strange feature that Schwarzschild metric has only one event horizon. But curved black hole has two event horizon. One is outer horizon and one is inner horizon. And there is a space in between the two. And instead of a point singularity, it's a ring singularity. And outside this outer horizon, up to a limit called static limit, there's a football-like region you can see in mauve color. This is called ergosphere. The static limit means if I put a particle or an observer inside this football region, this mauve color region, it cannot remain stationary. It has to co-rotate with a black hole. It should rotate with a black hole because there is no way it can remain stationary. In order to remain stationary, it has to move faster than the speed of light. So it has to co-rotate with a black hole. So this is one of the general relativity's most fascinating effects called frame dragging. So the production of the jet is strongly connected with the effect of frame dragging. So due to enormous gravity of black hole, their rotation forces the local space-time around them to rotate along with them. So this whole space-time rotates like a whirlpool. So if there is a gas fed into this region, so there is accretion disk, assume there is an accretion disk around this black hole, which is feeding gas, because the gas can go up to the event horizon, which is here, the yellow region. So then it will be dragged by this rotation of the black hole, frame dragging effect, so which is shown on the left-hand side panel. You can see if there are radial flows of magnetic field line, radially directed magnetic field line, they will not remain radial anymore, or radial flow lines will become spirals or twisted lines. So you can see strong frame dragging effects seen from the top. Now so what is the connection between frame dragging and black hole production, jet production? So this is what is proposed by Blandford and Zenak in 1977 in one of their very famous paper, which is called Blandford-Zenak model, which is shown in a very simplified manner. So what I have shown here is the event horizon of the Kerr black hole, Kerr metric black hole, and there is a magnetic field line which is mostly in the polar direction, so it's called a poloidal field line. One single field line I'm showing, which is connected to the horizon, connecting the horizon to some distant conductor, which is plotted here in the form of a plate-like thing. This you can think is a conducting plate. So this field line is frozen like this. Now, if the black hole is rotating, so these field lines will start twisting in the ergosphere because this field line will no more remain poloidal. It will develop a toroidal component, that is azimuthal component. Instead of only Z component, it will have an azimuthal component. And then it will look like a spring like this. But since this field line, end of the field line is frozen at one end, so there are lots of magnetic tension start developing. So this is like a conducting plasma, which I'm calling a conducting plasma at the end of the field line. So this plasma will feel a lot of pressure due to twisting of this field line, and after some time, when the magnetic pressure overcomes the internal pressure of this plasma, so it will start moving with the magnetic field line. So this will be like a spring-like things, twisting field lines propagate outwards from the polar region of the jet. That is the magnetic field, polar region of the magnetic field. That is magnetic poles essentially. Rotational pole and magnetic poles are mostly aligned in this object. And then this plasma will be propagated outwards at a higher and higher speed because of the extreme high amount of magnetic tension which will build up due to the rotation of this black hole. And then this will be collimated. You can see this on the right hand side picture. It's like a cone because this twist will be going outwards and it will expand like this. So then you will see naturally a conical region developing, which is called funnel. So there will be funnel on the top of this black hole in the polar region, and then along this funnel there are lots of high energy plasma will escape. So this is the mechanism by which the jets are formed. This is a very simplified mechanism. Okay. So okay, if you want to see this simulation, you can go to this YouTube. I don't know whether it's visible or no, whether you can log into this YouTube. It's a European Southern Observatory. If you go to European Southern Observatory website, you can see a beautiful simulation of this plasma process. Okay, so I will drop this. I think you have all gone through this. So this one thing I was trying to show you here. So there was a very interesting observation taken in 2018, 2 years back. So there was this neutrino ice cube neutrino detector in Antarctica, which is designed to detect extremely high energy extragalactic neutrinos. And this was one particular neutrino or a few neutrinos were detected in this ice cube detector, which has the energy of 300 tera electron volt in Antarctica ice cube detector. And this event gave a fundamental insight into the origin of ultra high energy cosmic rays. So these cosmic ray means there's extremely high energy particles, mostly protons, ions, electrons, and other exotic particles, subatomic particles coming from some extragalactic sources. But we don't know the origin of these particles. So this was traced back because you had a way of showing from direction from which this neutrino came. So this neutrino originated in a relativistic jet of a distant blazar. The blazar is a simple quasar where the jet is pointing towards you, very, very small angle towards you. So there is a lot of relativistic beaming and boosting effects. So this jet was directly connected with a blazar. So which clarified the role of relativistic jets in accelerating particles to ultra high energy. So that's why these jets are so important. So one can now begin to understand even the origin of ultra high energy cosmic ray, because this has been almost like a 100-year-old mystery which has never been solved, that what is the origin, what is the source or sources of this ultra high energy cosmic ray. Some of the cosmic ray particles have incredibly high energy, something like going up to 10 to the 20 electron volt. So this is no ordinary object can produce these particles. So there has to be some extraordinary energetic event like this blazar and a black hole sitting and accreting matter and shooting out these jets. But there is complete lack of understanding currently what process created this neutrino, because there may be lot of particle physics processes going on which in the jet, which can produce this neutrino. So I won't go into it, but if you're interested, one can go and read this paper in Nature or Science, whichever magazine it was published 2 years back. So this is a very interesting observation. Okay. Now I'll just show you some pictures, what we have done from our IUCAA. So we are mostly studying giant radio galaxies. So what is a giant radio galaxy? These are the normal radio galaxies, but extremely large scale size. So these objects are all 1 megaparsec size. So that's why we call giant radio galaxy. The total size of these objects are 1 megaparsec and above. And here I have my student sitting here, Pratik Dabhade, who is working on this problem, and he has discovered hundreds of new giant radio galaxies from his work done with GMRT as well as LOFAR, that is a low frequency array in Netherlands. So this is a very interesting area of research, what we are following here. So the origin of giant radio galaxies, why they are so big, and what is the relationship of these relativistic jets and on those large scale, what they can do, from what type of galaxies, what type of black holes these sources are being created, and what is the effect of these jets on the outer regions, that is the ambient medium. So this is one of the very hot areas of research which is going on in IUCAA. And I can just quickly show you some pictures. So here's Pratik Dabhade, who is sitting right next to me right now. And then we have some other people also working with us. Maushumi is there. Shishir was also working. He's a PhD student. He has finished his PhD. And then we have Shomok Rai Chaudhary and myself. And then there are other international collaboration. So now I just show you some pictures of giant radio galaxies. So these will look very similar to normal radio galaxies. Like you have a core and a bipolar emission, core and a bipolar emission. Everywhere you will see the same phenomena. But only difference between normal radio galaxies and this is, these galaxies are extremely large in size. Some of them go up to 5 megaparsec in size, which is incredibly large. So large, it is incredibly large. So it is very difficult to understand how can a jet propagate from the core, which is 10 to the power minus 5 parsec, to 1 megaparsec. So that means it is a scale of 10 to the power 11. So the jet remains intact over a length scale of 10 to the power 11, which is impossible to believe in any physical model currently, because you cannot produce such plasma jets in laboratory because they dissipate in no time, within few microsecond or millisecond, microsecond they dissipate and lose their energy, because that is the challenge of fusion plasma, how to contain these jets or high energy plasma for a very long time in a small region. But here you can see this is being achieved on an extremely large region, like 1 megaparsec. So this is the quest. What plasma physics is involved in these objects? What is the role of magnetic field? What is the role of fundamental particles in these jets? Are these jets made up of electron and positron? Are these jets made up of electron and protons? Or there are other exotic particles? What is the origin of the neutrino from these jets? Why we don't see gamma rays? Sometimes we see gamma rays, sometimes we see X-rays, sometimes we see optical. In what region of this jet we see this, and what these jets do ultimately when they fade away. So this energy, as you saw, is getting dissipated in the radio lobes. But these radio lobes are just a waste products. So ultimately these jets going up to megaparsec distance and mixing with the intergalactic medium from which another galaxy is forming. So perhaps these jets are creating magnetic fields in the intergalactic medium and helping in forming other stars and galaxies also. So this is completely unknown domain. So here is just like catalog of his objects. There's a whole catalog of hundreds and hundreds of objects. So you can talk to Pratik if you're interested and know about more of his. And he has recently submitted an extremely nice paper where he has reported hundreds of new discoveries of these giant radio galaxies. So these are just some pictures from GMRT. Here is a exotic looking giant radio galaxy, which has got a 2 megaparsec size. And the right side, you can see a huge mushroom cloud growing from the end of the jet. It's something like a nuclear blast. So when there's a nuclear blast, you can see a collimated jet, and then which dissipates into a mushroom. So it is exactly similar to that. So it's a very exotic looking object. We don't know the origin of all these objects. So okay, fine. So let me finish here. So I'll take some questions if you got, please. So Pratik can forward me the questions. Thank you for your patience.
Okay, so I'm going to. So Junik has a question, so I'll unmute him. Junik, please go ahead.
Hello, sir. Good afternoon.
Okay.
Hello, sir. Good afternoon.
Yes.
Thank you, sir. That was a fantastic lecture. Sir, my point is that those jets are really very interesting. So I just want to know how long does this jets remains active? Like they can go for several megaparsecs distance, but for how long does they remain active?
Yes. That's a very key question you asked. That is one of the key questions of this field. That what is the activity time of this black hole? Okay. Essentially, the jet will remain active as long as the black hole can produce this jet from its formation region. So now this is a very important question which is being probed through various methods, but current understanding is that most of the radio galaxies of normal size, not giant radio galaxies. Giant radio galaxies are megaparsec size. The normal radio galaxies are few hundred kiloparsecs in size, so 1/10 of the size of giant radio galaxies. So the jets remain active perhaps for a few million to tens of million years, 10 to the power 6 to 10 to the power 7 years. Okay, so that is the time scale for which the black hole emits jet, and for the reasons still not known, the black hole suddenly switched off this jet. So these jets are not everlasting. They are very short time scale phenomena compared to the time scale on which the galaxy has evolved. The galaxy has evolved on the time, or the black hole has evolved on the time scales of billions of years. But the jets, no way the jets can last for 1 billion years. So this is an extremely important question you have asked. That what is the reason that a black hole can remain active only for a finite amount of time and then die out? But then there is some other aspect of it which is even more interesting, that some of the objects you can see the jet being switched on again. So these are called double radio galaxies. So what you see in these objects, I don't know whether I can show you a picture. So like this picture you see here, it is not double, there is only single axis, one single lobe here, one pair of lobe. But in double radio galaxies, you will see two pair of lobes. One outer bigger pair of lobes, which is very far away from the central galaxy, and an inner pair of lobes. That means the black hole is again switched on due to some reason. So that means this black hole has some duty cycle. That is how long it can remain on and how long it can remain off. So there's switch on and off phenomena. So that's extremely important question. And we don't know the answer to this question. What switched on the black hole and what switched off the black hole? But the time scale can be of the order of 10 to the power 6 to 7 years. Thank you for that question. Very good question.
Thank you, sir.
Thank you.
Okay, so the next question is by Arjun, who has requested me to ask on his behalf. So Arjun asks, the energy of the particle is changing with the time, and the change in magnetic field is the reason behind this. So what causes the change in magnetic field?
I mean, the question, can you
This was in context of, I think, jets.
So as I understand you, perhaps you are asking what is the reason that particles are losing energy? In what way the particles? Okay, let me just try to answer your question, guessing what you are asking. See, there are two ways the relativistic particles in a jet can lose energy. So first, what we are calling relativistic particle. First I should tell you, there is a difference between a relativistic particle and a relativistic jet. The relativistic jet means the plasma moves at relativistic speed as a bulk flow. The entire, like a cloud, moves at a very high speed in a narrow cone. This is called relativistic bulk flow. Now inside this plasma there are relativistic particles which are moving with the plasma, but individually they have got relativistic velocities. That means their Lorentz gamma factor is very, very high, like 10 to the power 4, 5, even 10 to the power 6 and above. That means the relativistic particles we have to consider. So the jet is relativistic, which is composed of relativistic particles, but the particles are not moving all along the jet. They are moving in various directions, but mostly confined within the jet. Now the source, the mechanism by which the particle can lose energy is first is synchrotron radiation. So the synchrotron radiation has got strong dependence on the Lorentz gamma factor of the particle. That is the energy. So if the energy of the particle is higher, so it is the loss of energy dE by dt is proportional to gamma square. That means a particle or electron or a positron of high energy will lose energy much faster than an electron or positron of lower energy. So that means the high energy particle will be depleted very fast, and low energy particle will be depleted at a lower rate. So then it will be, if you see the spectrum, that is a radio spectrum, then you will see there is a loss of energy at high energy. So the high energy particles in a constant magnetic field also produce high energy photons, that is the synchrotron photons. That means if you have a high energy particle in a low magnetic field or any magnetic field, it will produce some relativistic photon. This is a synchrotron photon. But the same particle, when it loses energy, will produce radio emission at lower wavelength, lower frequency or longer wavelength. So then you will see there is evolution of spectrum. So then, of course, it's a function of magnetic field. So the stronger magnetic field can lead to more losses, and a stronger energy can also lead to more losses. And there is another process which I have not talked about. It's called inverse Compton effect, because all these relativistic jets are not in vacuum. They are surrounded by cosmic microwave background field. So this cosmic microwave background photons interact with the relativistic particle, and these relativistic particles can lose energy through the interaction with cosmic microwave background photons. So that is also a source of loss of energy. So it's a loss and gain process. Somewhere there is losing energy, somewhere there is gaining energy, like in shocks. Okay.
Okay, so there are many questions. So Arjun, I'll not be able to ask rest of your questions. So I'll request you to write directly to Professor Bagchi. He may answer you on email. So next question is by Madhusudan. I'll unmute you. Please ask your question. Madhusudan. I guess he's not around, so I'll ask his question. So all the supermassive black holes are rotating time. How do we know this if we can't see the surface?
Yes. Correct. That's a good question. Yes. We can't just infer by seeing a black hole. Like seeing means you can't see anything in a black hole. But how do we know that the black hole is rotating? So one strong indication, as I told you, is bipolar jet. Like you can see in this picture, there are a strong axis in this object. It's not symmetric emission. Now, if the emission was symmetric, then it would have been something like a spherical object without any preferential axis. But since there is a preferential axis, this tells there is a rotational axis in this object. Okay, so that tells very strongly that this must be a rotating black hole. And another factor is that the collimation angle is very strong collimation, that the axis of the production emission of the jet does not change in time. It remains constant for a very long time. So like suppose you see double radio source, one episode and then switch off. The second episode is mostly in the same direction as the earlier episode. That means the black hole is a gyroscope, that it is not rotating, it is not precessing, or it is not changing its axis. It is an extremely high angular momentum. So that again shows it's kind of rotating black hole, but it's very difficult to prove whether the black hole is rotating or no. But there are other methods which I won't go into it. You can use X-ray telescopes and infer more than this. But this is a very strong indication that there are spinning black holes involved in this process.
Okay, next question, Himadri. Himadri, are you there?
Hello.
Yes.
Yes, please ask your question.
Yes.
Sir, my question is that initially you showed that special relativity shows that we cannot see the complementary jet, but
Yes.
how can we see two jets coming from radio galaxies?
Yes. Okay. Very good question. Yes. So how can we see two jets while we can see only one jet in a quasar, right? So yes, the answer is that
Yes.
suppose, okay, let me go back to that diagram, then I'll show you. So my initial diagram, okay. So, okay, here. Now, as I told you, in the source frame, the emission is isotropic mostly, okay. It is emitting an isotropic radiation or kind of a not highly collimated radiation. But the reason that one jet is highly bright, very bright and Doppler boosted, but the other jet is faint, is a consequence that the jet must point at a very small angle relative to my line of sight. Okay, right? You understand that? The jet has to point to at a very small angle relative to my line of sight. Now, suppose I see this jet at a large angle. Suppose this red arrow that I'm seeing is here like this, or it's like this, or like this. Then this relativistic beaming effect will vanish. Okay, it will become very weak because there is something called Doppler factor. So this Doppler factor is strongly dependent on the velocity of the flow and the angle of the flow relative to your line of sight. So this is Doppler effect, the relativistic Doppler factor. So essentially, the relativistic Doppler factor will vanish if you are at the 90-degree relative to the jet direction. That means both the jets will be equal. There won't be any asymmetry in the forward direction and the backward direction. So as you come closer to the axis of the jet, then this forward boosting, what's called relativistic boosting, becomes extremely strong, and opposite side becomes extremely weak. So then that's why this blazars, what's called blazars, extremely highly energetic jets pointing directly to the observer, almost pointing directly to the observer. Then they are only one-sided jets, and they're extremely powerful in gamma rays. They produce a lot of gamma rays. So this relativistic boosting is the answer. So that's why radio galaxies are almost on the plane of the sky, because our line of sight is cutting the jet perpendicular. So we are able to see both the sides of the jet with equal intensity. That's the answer. So if you turn a radio galaxy at some small angle, then you will start seeing very different pictures. So that's why people believe that quasars are actually relativistic jets in radio galaxies turn at a small angle. Okay, so that is a question. Yes, that's a very good question. Yes.
Okay, so there are many more questions, but I'll just allow one more last question. Pooja, can you go ahead and ask your question? Pooja?
Yes, Pooja, hi.
Pooja, please ask your question. I guess not available, so I'll ask her question.
Okay.
She says that we know the content of the pressure cooker jets are vapor. So what is the content of the black hole jets?
Yes. So what is the content of the black hole jet is not really vapor. It is relativistic particles. Okay. So mostly we don't know actually the answer to this question. So it's a quest currently. What these jets are made up of. So there are two school of thought. One school of thought is that these jets are made up of pair plasma. There is electron and positron, pure pair plasma. So these are called leptonic jet, light jet, because the electron and positron are light particles. But another school of thought is that the jets are made up of electron and protons, no antiparticles. So it's still very difficult to distinguish from the properties of the jet whether it is made up of leptons and protons, like hadrons. So this question is still not settled. But apart from that, the jet can have pions, the jet can have neutrinos. The jet can have every possible zoo nuclear particle from the zoo of particles. So jets are just relativistic particles coming out from the black hole.
All right. So I think there are 2-3 questions which I have answered to you in chat.
Okay.
So if you have more, then I think you can directly write to Professor Bagchi and he can take it up. So
okay, thanks.